Hello, hello. So today I'm going to talk about confidential transfers that were built on top of Solana. This is a report by ZK Security. It might not be public at the time of recording this video, but it should be by the time I publish it. So there might be some changes with the report. But anyway, so Solana has confidential transfers. The TLDR, there's a lot of moving parts, but the TLDR is that it looks a lot like Zether, which was I guess, an older paper that looked at doing privacy transfers in an account-based model. So if you know, ZCash was the other way of doing it, which is more like a UTXO model where you have a shielded pool. And it sort of grows and grows because of nullifiers. And every time you want to know if you receive something, you have to sort of scan the blockchain because things are encrypted and you don't know who received what. So this is kind of like maximal anonymity, if you think. But it's not super practical user for like the user experience. And so some people are moving in a different direction and using this account-based stuff where you're not really hiding the accounts, but you're hiding the balances and the transfers. So you know who's transacting to who, but the balances are encrypted. And we'll see that it's encrypted with this El-Gamal encryption, which allows you to add ciphertext together. It's homomorphically, it's additive, or it's homomorphic for the addition. And it also, but the transfers are also encrypted, but you can see which accounts are sending to who. There is a more like a smaller anonymity set version of Zether, which allows you to have like a small anonymity set, like Monero. So not the total anonymity set of Zcash, but something in between. Usually you see things like 8-10 people in this you choose like 10 accounts and you re-randomize all accounts but two, I guess, the sender and the receiver. And it's very hard to figure out who is sending and who is receiving in this group of accounts. We had a report in the past on Silent Protocol. Actually, we have two reports on them where they implement Zether with this anonymity set. I think they had something like 8 participants every time. But Solana has, there's no anonymity set here. We know what accounts talk to what accounts. Maybe I can briefly mention what the encryption scheme is going to look like. There is somewhere, where did we write that? I think it's here. No, it's not. Encrypts, no. Key pair, let's look for key pair. All right. So they use not the El-Gamal encryption scheme, but the twisted El-Gamal encryption scheme. My understanding is that it's nice because your ciphertexts look like Pedersen commitments right away. So basically, if you want to generate a key pair, it's kind of weird, but you generate random S, and here you raise H, the known generator, to the inverse of S. It doesn't really matter, actually. You could use S here as long as you use the inverse of S in other operations. But this is how it's defined in Solana. And to encrypt something, an X, you do a scalar multiplication with a known generator. Of course, usually G and H have independent discrete logs, and you don't know them. This is how Pedersen commitments are secure. And then you hide this encryption. We're going to say that XJ is almost a message. It's hidden in the exponent or scalar multiplication, but we're going to pretend it's the message. And we hide it by adding it to R, which is random, times H, which is our known generator. And here, this is an encryption, and we can give someone a decryption handle. And you'll see that in the protocol, they usually have one ciphertext, so they call this a ciphertext. It looks like a Pedersen commitment. And then they'll give decryption handle to different people. So everybody will be able to generate this RH without learning the R, which is why you can encrypt to several people with the same stuff. Don't think too much about that for now. And the decryption handle really looks like R times a public key. And you can see basically what we're doing is that we're processing the RH. You can see that as we're deriving some randomness here, RH. we're computing it, but it's still blinded by the S inverse of the owner of that public key. So when the owner of that public key comes and wants to decrypt it, they remove the inverse of S by multiplying their decryption handle with S, which cancels the inverse here, and we're left with RH. So we don't learn R, but we learn RH, and we can subtract that from this thing here to get X times G. If it doesn't make sense, just pause the video and think about it. What's important here is that there's different versions of El-Gamal, but every time you want this additively homomorphic version of El-Gamal where you can add ciphertext together, and it will just, if you add C1 and C2, you'll get an encryption of X1 plus X2. And you can even add something that's not hidden. So you can add something that you can add C plus 5 times G, and it's also going to work. You don't need to have something else that's also hidden. And whenever you do that, your message is hidden in the exponent. It's committed X times G. If you had a version of El-Gamal that was homomorphic for the multiplication, then you wouldn't have that issue. But here that's what we're dealing with, and of course we're doing this because we want to add transfer amounts to encrypted balances or subtract them when you're sending something you want to subtract to your balance. So this is what we're interested in, additively homomorphic schemes. What else is there to say here? Okay, so once you decrypt this, you're left with XG, and so you still have to sort of brute force and find that X. Of course there's all these schemes to find the discrete logarithm of something, especially when that something is small, that X is small. But it's important that it's small. And since tokens in Solana are 64 bits, basically what they do is that they'll split it between, well, initially the idea is to split it between the low 32 bits and the high 32 bits. So you can decrypt that, but you'll see that because people send you money, these chunks of 32 bits might get bigger, and so they do things a bit differently, where the low bits are 16 bits, and the high bits are 32 bits, and transfers are capped to 48 bits. But really, the idea is to have this to split a big number into chunks of bits that even if they grow, they're not going to grow too much, and you can decrypt them by solving for the discrete log. And you'll see that because we do all these things, we need to figure out, we're going to have a bunch of range proofs to make sure that the chunks are of the correct size. And these range proofs are going to prove that on commitments. And also range proofs, if you're subtracting some, we don't know if you have this, I want to send you 5 tokens, and in my account, there's only 4. We're going to compute the commitment of 4 minus the commitment of 5. And we're going to check if the new commitment we have is in a range of 64 bits. So we do these range proofs sort of all over the place to check these kind of things. Anyway, before I get too much into the details, I mean, this is the high-level idea, and I'm sure a lot of people could just take that and build the Zether scheme or what Solana is doing, and basically go from here to the final scheme, because this is really the core of it. Right? Every balance is encrypted with this thing, and you're encrypting transfers, and then you're subtracting, adding, doing range proofs. This is all there is. But of course, there's a lot of complexity. Devil is in the detail, and we're going to dive into that. So there's 3 repositories that mostly encompass all of the complexity of this protocol. We're looking at ZK-El-Gamal-Proof, which is really the ZK SDK of Solana, or the crate name is Solana ZK SDK. And in it, we're going to find some encryption stuff, the range proof stuff. By the way, if you don't know what a range proof is really it's proving that some commits to a value that's in some range. And usually we're going to do ranges that are going to look like from 0 to 2 to the 32, from 0 to 2 to the 16, from 0 to 2 to the 64, these kind of things. Sigma proofs. So we have a bunch of Sigma proofs. If you don't know what a Sigma proof is, it's like the 101 of zero-knowledge proofs. These are the first thing you learn about when you start learning about zero-knowledge proofs. They look like a Sigma Greek letter. So there's a prover message. then you receive a random challenge from the verifier usually, and then you send a final prover message. So it's a three message protocol, and you can do a lot of things with this kind of Sigma proofs. So here we're going to prove that a ciphertext was encrypted correctly. Actually, we have a list of the Sigma proofs here, so I can just go through the Sigma proofs. Usually the description looks a bit complicated, but here we have a nice compiler for these Sigma proofs, and maybe I'll talk more about that. But just to high level, to keep it high level, what we're looking at is a Sigma proof to prove that you know the private key behind a public key, a Sigma proof to prove that behind an encrypted balance, there is nothing. It's a zero balance, so that's going to be useful to close an account. We have a Sigma proof for ciphertext validity, meaning that we know that something that was encrypted. So that's the encryption here of X blinded with R. We know that, and we have correctly produced decryption handle for a number of parties, and these parties are going to be the sender, the recipient, and you'll see that there's also an auditor party that also receives the decryption handles because they need to be able to regulation stuff, or they need to be able to see all the transfers to if there's some fraud or something like that, they need to analyze what's happening. A lot of confidential transfers protocols do that these days, mostly because if you don't do that, you end up with legal issues. For example, what happened with Tornado Cash, and I don't know if the developer was sent to jail or something like that, but yeah. We have this batch version. It doesn't matter too much for now. Ciphertext-Commitment Equality, that's an interesting one. Sometimes you receive something, you want to prove that you can decrypt it. So it looks like this. That's the decryption. I think here it should be a minus, by the way. Oh, no. That's because sorry, it's not a minus. You're proving that the ciphertext looks like that. But since you don't know the R, you cannot use that as a Pedersen commitment. And when we want to do range proofs, we need a Pedersen commitment that looks like this, where you know the R. So we're going to use this kind of ciphertext commitment equality a lot whenever we want to do range proof on some balance or some amount where we don't know the actual full Pedersen commitments, but we can decrypt the value. We'll prove that the decryption, what is decrypted here, the X, is the same as a new commitment that we're going to create and that we can use to do a range proof with. So very important. Ciphertext equality. Basically, that proves that we have something and we're re-encrypting it to someone else, and we did it correctly. And percentage with cap, this is basically the most complicated one. This is an OR proof, meaning that it proves one Sigma proof or another one. So basically what happens is that you fake the other one whenever you prove one or the other. If you want to learn more about how that works, we have a great blog post. Sunil found a bug on that a while back, and he explains exactly what Sigma OR proofs are, how they work. It's really interesting. It's pretty short. I advise you to read that one. The TLDR is that you do receive a challenge from the verifier, but you split that in two. So you have challenge 1 plus challenge 2 equals the challenge received by the verifier. And so one you can fix. So imagine the verifier challenge is equal to 4. You can fix one, it's 3. And so the other one is going to be 4 minus 3, it's going to be 1. But of course, we're dealing with large numbers. And so when you can fix one, you can simulate that proof. It's sort of like that challenge in advance. But since the other one is basically random because it's the actual challenge minus the fixed one, you cannot simulate the other proof. And so you have to actually produce the other proof. But you have to choose which proof you want to simulate and which proof you want to take. So you have two Sigma proofs within an OR proof, and one is the correct computation of a fee. So here we're going to compute a fee, and I'll explain more about that. The other one is basically if the fee is like going through a maximum fee, this max fee value, we're just going to prove that the commitment to the fee is equal to that max fee. without revealing that we reached the maximum fee, because we don't want to leak anything about the amount. All right, so at a high level, these are the Sigma proofs. And if we look back at the code, they're here. So there are a bunch of them. And then there is a ZK-El-Gamal-Proof Program. And basically all of these proof stuff is going to be exposed on Solana as a program, so a smart contract. And part of that is here. And so this defines sort of the API of verifying these proofs and what it looks like, specifically the serialization on Solana. And Solana, you can look at it here, but Solana uses these pod things, and you can derive the serialization of these pod stuff. And I'm not gonna go too much into that, but that's how Solana the Solana VM works, which is based on eBPF, but that's not very important. What else is there to say? Okay, maybe one thing to know is that the fiat chimization, and there's a bunch of stuff that are not very secure if you just look at the actual things here. But if you look at the wrappers, then they do things correctly, because they start the transcripts here by absorbing all of the public inputs. So I don't know. Here, this is the Ciphertext Equality Proof context. Context here is just the instance, the statements, the public inputs. And so you need to absorb that into the transcript, and this is where it's done. So it's not done inside the actual verifier functions, which is one of the things that we told them. It's not a problem with Solana itself, because Solana uses it securely. But if someone were to extract that code or use it as a library, then that needs to be something that they're aware of. All right, so just continuing my high-level presentation of all these repositories. This is the first one, ZK-El-Gamal-Proof. By itself, it's not enough. There is one file on the Agave full node. So this is the full node code for Solana. And in ZK program / ZK-El-Gamal-Proof, you have this lib file that basically exposes all of these functions as this ZK-El-Gamal program or ZK-El-Gamal-Proof program. And this program is going to be a built-in program, meaning that it doesn't run in the VM, the Solana VM, as an eBPF program. It actually runs natively. So whenever people make calls to the functions or the instructions in this program, they're gonna get all of the. My understanding is that they're gonna get all of the VM. The host is gonna run them and then return to the VM with the results. And so because you're doing that, you need to hard code the compute units, which is the gas of Solana, and to understand. Basically, these are all the instructions or the functions of that program. And we're associating them with the cost of running them, so that the sender, the creator of the transaction, has to pay that cost. In it, you can see all the instructions here. So this is how Solana works. You send a transaction, and that transaction has many instructions. And one instruction allows you to verify a proof of different types. You also have an instruction to close a context state account, and I'm going to come back to that. But this is basically the one file that exposes the ZK-El-Gamal program, a ZK-El-Gamal-Proof program, as a Solana built-in program, so that the Token-2022, so the actual confidential transfer program, can verify proofs. And so finally, we go to the Token-2022 standard, which is a program that allows you to everybody on Solana seems to be using the same program to launch tokens. And in that program, there are extensions. And there's 3 extensions here: confidential mean burn, confidential transfer, and confidential transfer fee. And basically, in Solana, you'll see you can create tokens in this Token-2022 program. You can create tokens. Every time you create a token, basically like a new token, like OneCoin or like whatever, you create what they call a mint. And so you'll extend that with a confidential mint if you want your token to support confidential transfers. And if you're a user, you'll have to create your own token account. And so you'll have to create a token account that's one token account per mint. So if there's 2 different coins, you'll have to create 2 token accounts for yourself for these 2 mints. So it's not like Ethereum where the program has a state that it can mutate. Instead, accounts in Solana are either program accounts or data accounts. So if you're a program account, you're using your data field just for the program. And this means you have to use other accounts' data field to store data that's interesting to you. So everything in Solana is an account, but you cannot have an account that has a program and data. You have to choose. And so it's really interesting because you'll see when we look deeper at this that whenever it wants to store a mint or it wants to store a token account for user for a specific mint, it basically creates new accounts and it points to these accounts by being the owner of these accounts. And that's how it can mutate the data in these accounts. So everything is an account, and you can see different accounts as like blobs of data, and understanding how you go to an account as like kind of a hash map where you have to figure out the key, which is the key of the account, and then you can read the data of the account. So anyway, if it's not clear, just read some basic foundations of Solana programs, but maybe that becomes clear through this video. Okay, so maybe let's go back to the core things. Maybe I can talk more about the Sigma proofs. I've talked about the twisted El-Gamal encryption scheme. I think that's clear enough. The Sigma proofs are interesting because here we use the Solana protocols doesn't use that compiler, but that's what we used in the report to make things clearer. Dan Boneh has this compiler here to compile Sigma proofs very easily through a homomorphism psi here. And basically it tells you like, if you have a homomorphism psi, then this is what the proof looks like. This is the prover message. This is the verifier message. Verifier message is always just a random value. And then this is how you construct the final prover message. And this is what the check looks like at the end. So this is a very nice formalization. And if you understand that protocol, there's a proof that it's sound and complete and all of that. And if you understand that, then you can just sort of specify all of your Sigma proofs with a very short, succinct description that looks like that. And so maybe here I can read that with you. It always looks like the general shape without looking at this, like this doesn't really matter. But if you know Schnorr identity protocol or Schnorr signatures, this is what this is basically. And so let's look at public key validity. If you remember, we wanted to prove that we know the S behind a public key, or really the S inverse behind a public key. And so everything is going to look like that, where the homomorphism psi, which we'll define, of some witness is equal to some instance. Okay, so homomorphism of witness equals to instance. And that's all you have to define. And then you get a magic protocol out of nowhere. Here, basically, it says that this is your homomorphism. You just multiply your value with the generator H. That's how you get the public key. And then you just compare that the instance is just the public key. Super easy, right? For the zero check, the witness is still the secret key. And here we multiply it with P to show that it's equal to H. So we did it the other way around. So we want it. This is basically a public key validity, right? Like we have a public key validity check inside of this zero check, and we're proving something else. And here we're showing that S times P is equal H, which is the same thing as showing that S inverse H equals P. And the second thing we're showing is that S times D, so the decryption handle, correctly gives us the ciphertext. Meaning that the exactly. Meaning that the ciphertext is the encryption of 0. Because the decryption handle should give us just a randomization that's added to the ciphertext, to the value. And if the randomization added to the value is the ciphertext, then the value is 0. So we're effectively proving that it's 0. Group ciphertext validity. So here we're proving that, okay, R and X. And here we're basically showing that we can compute that, which is the ciphertext. So we know the R and the X behind the ciphertext, and we're going to reuse that R to compute the decryption handle for all of the public keys and compare that to the decryption handle of the public keys that we're deploying on chain. So again, it means that we know the decryption of some X, and the decryption handle for all these public keys are computed correctly. So these are the complete, you can imagine just 1D, for example. These a decryption handle, and is correctly computed as RP, with P the public key. There's a batch version because remember we're splitting our amounts between the low 16 bits and the high 32 bits for a 48 bit value. So we can batch that by using a random challenge, but that's not very interesting. So I'm not going to talk about that. And but it's a random linear combination like we always do. Ciphertext-Commitment Equality. Your witness is the private key, the encryption, the value encrypted, and the opening. So you prove that you know the private key. So this is a public, public key validity. Then you prove that the thing is encrypted correctly, and then you prove that your new Peterson commitments, which you know the opening of, is encrypting or committing to the same X as what you just decrypted. Ciphertext equality basically does the same thing. You're proving that you know the public key, the private key behind the public key. You're proving that you know X, you can decrypt X correctly, and that X is the same as some other encryption, and the decryption handle is done correctly. And percentage with cap, that's the tricky one. Sorry for going fast, but you can always pause the video. Percentage with cap is basically, we can look at the easy one. The easy one is that the commitment to the fee is equal to max fee times G here. I feel like we're missing the random part here, but I'm oh no. So sorry. So if you take the commitment and you subtract the max fee times G, what you're gonna get is only the blinding thing, the RH, and so that you're proving that what you're computing here is equal to that RH. So you know the opening to that thing, and that thing is exactly the max fee. And the fees a percentage, that's the tricky one. You're trying to prove that BP times the amount divided by 10,000 is equal to your fee. The problem is that when you divide by 10,000, that's not always going to be, it's not always dividable by 10,000. And so you cannot divide by 10,000 because we're in a field. So what they do is, maybe I can write here. I'm not going to modify that. What they do is, again, we want the base points. So it's it's a fee, rate times the amount divided by 10,000 is equal to the fee, right? This fee here. The problem is that you can't always divide by 10,000. So if you want things to be correct in a field, it has to be correct in the integers. So what we do here is that we add some delta with delta in 0, 10,000 to make sure that we correct this value so that it's dividable by 10,000. And so we can rearrange this like this, which looks exactly what they have here, right? Well, they take that and they move it here. So that they prove that proving that delta is in between 0 and 10,000, and proving that the fee and the amounts are in the correct ranges as well. So if delta is an incorrect delta, is just a bullshit delta, we're gonna get stuff that is in like outside of the range. These are not gonna be 64-bit values. And so you see that basically we do range proofs for all of these things outside of the sigma proof in the protocol. Cool. Okay, maybe I'm gonna stop here with the sigma proofs, and I'm gonna talk about the range proof. I know this is a lot, but this is another, we're disconnecting from that and looking at the range proofs. The range proofs are built on Bulletproofs. So Bulletproofs is a paper. Interestingly, it comes from the same group as Zether. That's interesting. And Bulletproofs is basically an inner product argument. So it tells you that you can prove, where is it? You can prove something like that a vector, the inner product between two vectors is equal to something else when you have commitments to these things. So you don't know what they look like, but you have the left input, right input, and you want to prove that it's equal to this final thing. If you don't know what an inner product is, basically it's the first, if this is A and B and this is C and D, the vector C and D, it's A times C plus B times D. It's the first entry of both vector multiplied, then the second plus the second entry of both vector multiplied, plus the third entry of both vector multiplies, etc. It's you could say it's an Hadamard product of the two vectors, so pairized multiplication, and then you add all of the entries of the vector. You sum all the entries of the vector. That's another way to see it. Anyway, so Bulletproof is this protocol. It allows you to do that, these inner products, in a way that doesn't require trusted setup. So unfortunately, the complexities are not as great as Gross16 or KZG and these kind of things. But no trusted setup, so that's cool. And with it, you can do like PCS, polynomial commitment schemes. For example, if this is the coefficients of a polynomial, and if the right-hand side are the powers of a point you want to evaluate at, then this would give you the evaluation of this polynomial at this point. Or you can do range proof, and this is basically what this note explains. It's also part of the Bulletproofs paper, but I think the Dalek library, which is the one they use in Solana, has a very good explanation. Actually, they don't use the Dalek library. They use it for some stuff, but they extracted the range proof stuff because the Dalek library does a lot of things, and they just wanted to do these specific things. So if you look at the code, you'll see that range proof actually has the code for an inner product and the code for the range proof. But the note, it looks a lot like the notes from Dalek, so we can follow that. I'm not going to explain that too much, but basically you can see that you can do a range proof if you have a value v, you want to prove that it's in between 0 and 2 to the n, not included. You can show that the bits of a basically multiplied by the power of 2. This is a binary decomposition, and you can prove that the binary decomposition of like, I don't know, 32 up to 32 bits is equal to the value. This is how we do range proofs in like R1 CS circuits as well. So this is very similar. And of course, you also need to prove that this bit vector is actually composed of bits, 0 and 1, since we're in a circuit. So you also have to prove this thing. And you have this whole protocol that I explain in this post on my blog, high-level intuitions for the Bulletproofs IP protocol. So I'm not going to explain that again, but actually this is for the Bulletproofs IP protocol, not for the range proof. But I also have 2 videos on the range proof where I explain the intuitions. So, just refer to that if you want to learn about that. I'll post that under the video description. So yeah, and just the range proof basically is this kind of protocol, and eventually in this protocol they end up using Bulletproofs, the inner product. So they end up using a proof of this inner product. So they sort of create these equations, and eventually you have to do some inner product arguments. It's pretty, I mean, the code is very clear. I don't know. Maybe I'm not gonna go over it because I made these other videos. So I'm gonna ignore that. Yeah, maybe I'll talk about the token 2022 now, because this is a big part of the of this protocol, of course. In the report, we have an overview. Maybe I can go through some of that, where basically we talk about how these extensions work. So an extension, so we have these base types. I already talked about that. There's a mint base type for every new token, and there's the account base type for token accounts. So if I want an account for a new token, specifically for that token, I'll need to create this token account. If you look, so these are accounts that are owned by the Token 2022 program, so that it can mutate the data, and nobody else can mutate that data. So usually, what you do, it doesn't matter too much, but what you do is that you allocate some accounts, you allocate the right size for the data, because you have to pay for that account. There's this notion of rent in Solana, where based on the length of the data that you can initialize with zeros, you have to pay for that. And if you close your account, then you can take that money back. And so what you do is that you allocate that account with the right size, with the right rent, and then you assign that account to the token 2022, so that the token 2022 program can own that storage account. And then it will use the data field of that storage account and use that for storing either the mint of your or your account, token account. And so the data field will always look like a mint or an account, and then extensions using this TLV tag length value encoding, where you have a tag, then you have the length, and then you have the data, and then another tag, then length, then data. And you can think of it like when you're trying to figure out where the extension is, you'll basically go sort of like a linked list. You look at tag length. If it's not the tag you're interested in, then you jump the length, and so on until you find your extension. Okay, not super interesting, but as I said, there's 3 main instructions that are added: confidential transfer extension, confidential transfer fee extensions, to add fees, confidential fees on top of that. So you can just use that if you want, but if you want to have confidential fees and being able to pay fees in confidentially, you can add that. And finally, you have the confidential mint burn extension, which allows you to mint and burn in the confidential world as well. So this is very similar to ZCash, where you have a shielded pool and you have a non-shielded pool, and you can sort of, whenever you create a token, actually with that extension, you'll mint in the base token, and then you have to deposit this in the shielded world, in the encrypted world, and you can then withdraw back to the base token. So you can have tokens in the clear and confidential tokens, confidential transfers. Maybe we can say CT, confidential transfer. So you have the base world and the CT world. And you can basically prevent the base world from existing. Every account can disable it, but you can disable it at the mint level by enabling this extension. So if you enable this extension, you will always mint in the CT world, in the encrypted world, and nobody can move back to the base world. So that's interesting. Every instruction has sub-instructions. So if you just look at the confidential transfer instruction, you have a bunch of sub-instructions. And these basically, they mirror the base token. So for base token, you have like initialize means, you have transfer, you have stuff like that. No, here we want to do the same for the confidential token, and note that the balances will live in the extension. So there's an extension called confidential transfer mint for the mint and confidential transfer accounts for the accounts. And the balances, the encrypted balances, will live in this confidential transfer account. So in one of these extensions for an account type. And so there's nothing much to say here, but what I can say is that usually you'll want to, the way it's implemented is that you'll initialize extension on the mint first, any extensions, not just confidential extensions, and then you'll initialize the mint. And at this point, once you initialize the mint, you cannot initialize any extensions anymore. So like that, you cannot surprise users. But for tokens, you have a configure account. I think it's missing one. There's configure account with registry, which I forgot to add here. But there's a configure account, and here you need to enable your token account first to initialize it first with the base instructions, and then you can call that to initialize the extension. So it's the other way around, but it doesn't matter too much here. And this will basically create this big ass struct in your data, extended data in your as I just explained. And here you can see there's an approval. Doesn't matter too much, but accounts are not necessarily approved automatically when they join a confidential token. You have your El-Gamal public key, so you can encrypt your balances and people can encrypt transfers to you. There's a pending balance. Maybe I can mention, I'll talk more about that, but maybe let me finish. This is your encrypted balance. This is just a field where you put some AES encryption of your balance. This is just for you, so you have somewhere to store it, so that when you want to you have a new client or something like that, a new wallet, you want to be able to decrypt your balance, you can do it directly here by just symmetrically decrypting your balance with your key, so you don't have to do too many brute force or discrete log solving. And these are just flags. I talked about allow non-confidential credits so that you can not make any mistakes and make sure that you'll never use the base token, and you have some other stuff. What else can I talk about? What's important is that you're in this world where you're extending a base token, so it's important that it's done in a way that's correct, and you're also playing with other extensions. For example, here we listed the posable config, transfer fee config, non-transferable account. These are all extensions on the Token-2022 program, and so you need to make sure that these extensions still play nice with confidential transfers. So I don't know if the mint is posed, but with the posable config, then the confidential mint is also posed. Okay, I'll explain more. I think the pending stuff is interesting. Maybe I'll talk about that. So whenever you make a transfer, you have to create a proof. And so you want to make sure that when someone sends you a transfer and this gets aggregated in your balance, it doesn't invalidate your proofs. And so every time you make a transfer, someone could maybe front run you and just send you some money and update your balance, and it would invalidate your proof. Because you're creating these range proofs and sigma proofs based on a specific balance, right? Encrypted balance. So to avoid this issue of denial of service, we basically have a pending balance where people will send, whenever someone sends you something, it will get aggregated and accumulated in this pending balance. And then at some point, there's a instruction called apply pending balance that allows you to take that, or what you think that is, the expected pending balance. Yes, I don't know why it's called counter. Oh yeah, this is using a counter, but you're expecting the pending the pending stuff to look like something, but actually someone can still modify it, right? But that shouldn't matter. So you need to track what you expected versus what was the actual thing just for you. You can think about that. But basically, there's this apply pending balance that will allow you to aggregate whatever is in there into your balance. And the fact that it's in there and that you can do that, and that there's this pending balance that's split into these bits, allow you to decrypt what people are sending you by solving a discrete log on smaller values, and then add it to your balance while updating this thing, which is an AES SIV, actually AES sieve. So this is AES GCM, but with basically things don't break dramatically if you reuse a nonce. This is really a tangent, so I don't want to talk too much about it, but there's this ASC standard, and you can look into it if you're interested. But anyway, I think this is enough. Maybe I can also mention that there's a counter because you don't want things to blow up too much. Usually this is set to 2 to the 16. So if people send you 2 to the 16 transfers where the pending, for example, the low part of the pending balance is always a 16 bits, or I mean of transfers is always 16 bits, then this will at the max get to 2 to the 32, and then it will block more transfers so that you can efficiently solve the discrete log. Here, this might, since it's a 32 bits chunk, this might get to 48 bits, but I think they're basically estimating that it's not going to happen. And worst case, if it happens, you can try to decrypt individual transfers because you can still see the ciphertext for these individual transfers instead of trying to decrypt the aggregated balance. So you always have a way to decrypt things individually instead of decrypting the aggregated balance. Anyway, before I look at the code, I just want to briefly go over the other extensions, the two other extensions. So if you have the base fee extension on your base means, then you will automatically have this confidential transfer fee. Automatically meaning that if you don't have it, it won't work. So it forces you to use that. The way fees work is interesting because in Solana, things are done in a highly parallel way. And so you don't want to be in a world where every time you pay fees, everybody always use the same fee collecting accounts because that would lock the same accounts. Like if all these transactions would always lock the same account and you wouldn't be able to run them in parallel. So instead of doing that, what they do is that they add this confidential transfer fee amount extension to all the accounts. And this is basically an encrypted balance, which stores fees as they were received in the individual token accounts. So if I send you money, the fee will be calculated and subtracted from the amount that I'm sending you and stored into this fee extension in your account as the recipient. Then you have these fees everywhere, which by the way, you cannot close if you want to close your account, you will have to remove these fees as well. And these fees need to be harvested, which is a permissionless. So harvest withheld tokens to mint. It's a permissionless instructions. If you want to close your account and there's still fees in your account, you can call that to move these fees to the mint authority, which is here. This is an extension added to the mint, which has a balance here, which can collect fees, and then you can use another instruction to send them to the withdraw withheld tokens from mint and send it to an arbitrary account. And this looks basically like transfers. And harvesting is not as bad because it's just one transaction that will lock a bunch of accounts, but it's not that bad. There's this notion of referring to accounts as read-only and write-only, and a lot of read-only can if a bunch of transactions use the same account in read-only, it's fine, they can run in parallel. But if they use it in writes, then we have to lock. And here, this needs to write because we're going to set that to 0 when we harvest fees. Okay, anything else is not super interesting, so I'm going to skip that. And then finally, we look at the confidential mint burn. This is the last instruction that has all of these sub-instructions. But basically, just to remind you, this allows you to mint in this confidential encrypted world and to disable minting in the base world. And so you have initialize mint to initialize the extension, and then you can mint and you can burn. These users can call to burn. Since users call that themselves, then the authority needs to call apply pending burn, because you might guess burning is kind of like transferring, and so this will transfer a negative balance to the authority, to the pending balance of the authority, and so this will need to be applied into the confidential supply, but encrypted balance, which tracks all of the total amount that was created. And so when you're minting, it's the same as a transfer, except that you'll encrypt a positive amount to both this one and to some accounts. So it really looks like a transfer. And that's basically it. Like we talked about how it's supposed to play nice with other extensions. Initialization and interaction between confidential extensions, I've sort of talked about it. You have to be careful about how you interact with base operations and stuff like that. So this is not too interesting for us. And yeah, this is the high-level overview. And I think now we're ready to look at some code. So I don't know how long I've been recording this for, and I'm talking about a lot of things, but I want this to be exhaustive and I want it to be useful if I were to look back at the code in like, I don't know, 10 days, a month, a year, or something like that. Yeah, all right, so let's look at the code. So Token-2022, there's the program. A lot of the stuff is in confidential as well. We have ciphertext arithmetic, so that's when we are homomorphically adding ciphertext or subtracting and or scaling and these kind of things. If you look at the code, you'll see there's not too much stuff, but what's interesting is that they handle ciphertexts, which is both the Pedersen commitment, I guess, and the decryption handle. And both of these things are homomorphic, so you can, because you have to update the decryption handle as well when you're adding to a balance. So we can look at it, I guess, but you'll see that it's the length of the Pedersen commitment and the decryption handle. So again, the commitment is like x times g plus rh. So that's the first part, and the second part is the decryption handle, which looks like r times p, the public key, where p is really s minus 1 times h. And so someone that would multiply that with s would get r times h, which they can subtract from here to get this value, right? Okay. So this is just arithmetic. There's an El-Gamal registry. This is not too interesting, but basically, if you wanted to send tokens to someone else, but they don't have a token account for a specific mint, because they have to create a new token account for every new mint, they can preemptively publish a... so this is a program, right, that people can use, and they can publish... I don't want to look too much at the code, but they can publish a public validity proof. They can publish that tied to an honor. So basically, the data will look like a public key and an El-Gamal public key that was proved to be valid. And people can reuse that to create an account for you without knowing your private key, right? Because to create an account, we'll look at that. I mean, I can look at it now, actually. Because to create an account in confidential transfer, by the way, everything is always in processor. That's the on-chain logic. To create an account, we look at process configure accounts. We have a function for that, but we have also a function with registry. So this is tied to the El-Gamal registry that we're looking at here. But in both of these, they end up calling process configure account, and you'll see that you need to provide a public key validity, proof. And yeah, it's here, public key validity proof. So of course, if you don't know the private key, you cannot create that proof unless someone has published it in advance and added it to this registry. But it's not too important. You can sort of ignore that for the most part. Proof extraction is basically, that's interesting. I'm going to mention that next, actually. I just want to say proof generation, that's the client-side stuff. So here, it's pretty straightforward. You just need to make sure that you're using a cryptographic random generator whenever you create these R openings or blinding factors, some tests. So this is sort of segregated in its own folder, but most of the logic is inside this extension confidential transfer, the main extension or the main instruction, confidential transfer fee to add fees, and confidential mint burn to add minting and burning to your confidential transfers. So always processors, if you look at the end, you'll always see the main function process instruction that looks as the input of the instruction. So again, a transaction can be many instructions. So this is just one of the instructions that we're checking, and you'll see that it just looks at the first bytes, input 0. The first byte looks at what is this instruction, and then it routes the logic to the correct function. So here, if you have an initialize mint instruction, then we'll route to the process initialize mint. I'm not going to go over all of these functions, but I want to go over a few of them just to show you the patterns that we see when we look at this kind of code. You always see the arguments to the function. And so these arguments are, I guess, deserialized from the from the instruction data, the input to the instruction, and every instruction has what they expect the instruction data to look like. And every instruction not only has input data, but it also has accounts. And this is a list of accounts that they will read or write to. And basically, these are just pointers essentially to the transaction list of accounts and the transaction list accounts in a specific order. I don't remember it. I think it lists accounts by signers and then non-signers, where signers are accounts that have to sign the transaction. So this is interesting because you'll see, but the program itself can say this account needs to be a signer. And if this account is not a signer, then, abort. And so you'll have these kind of accounts. And then signers or non-signers are also divided between the first accounts in both vectors are write read and then read only. So you're really differentiating write read from read only. And this is important because you'll see that if you don't own an account, you cannot write to it. And so this is really eBPF stuff, or the way they run their VM. They'll load the account in memory, all the accounts. And if it's a read-only account, they'll read it in a special way. If you try to mutate the account, it's loaded as read-only, it will crash. So it will abort the whole transaction. If you have an error in just one instruction, it will abort the whole transaction. Okay, so before I look at that, I just want to say that there's one pattern that you'll keep on seeing, which is in what I hinted before, which is in the proof extraction. And basically what's going to happen in every case when you're trying to verify a proof. Ooh, shit, I forgot to mention that. Okay, so I'll mention that again, but I forgot something on the ZK-El-Gamal-Proof Program. But I'll talk about that first because we're here and I don't want to take too many tangents. So whenever we want to verify a proof as part of the logic, for example, in the process initialize means, actually there's no proof. Okay, when we create an account, I said that already. There is a public key. Where is it? When we want to configure a token account, initialize a token account with the confidential transfer extension, will require a public key validity proof. So we'll call this function verify and extract context, which is right here, with the type of the proof. And then we'll get the context, which is the instance or statement or public inputs, which here only contains the public key, right? We're proving that we know the private key associated with that public key. So that's the only public input. Whenever we want to verify such a proof, we'll use that function, and what it will do is that it will look for where the proof has been verified. it either has been verified in another instruction somewhere in our transaction. So that is the case if we pass a proof instruction offset that is not equal to 0, we will do some instruction introspection, which is a feature in Solana, which allows you to look for other instructions given an offset. And the sysvar account, which is a special account in Solana that's only read-only. And it will look for an instruction of a verification of a proof for your proof type, for that proof type that you passed. So here it's a proof, validity proof, public key validity proof type. If it finds one, it will look at the instruction data and it will extract that instruction data which contains the instance or statement or public input. And it will return that. So that's what it does here, and it returns the U. The U here is the second type parameter, and you can look here. The second type parameter is the this structure. But if you don't pass that offset, it means that the proof was already verified before, and the fact that it had been verified was stored in some temporary account. And so that's what I forgot to explain, but maybe it's better to explain it now because it's just in time. We're looking at these concepts. And so remember, we had a bunch of instructions to verify different types of proofs, but we also had one to close the proof context accounts. And if we look at when we verify proofs, there's two tweaks that you can do when you verify a proof using the ZK-El-Gamal-Proof program. That's a built-in program. The first tweak is, where is that proof? You can pass that proof as part of the instruction data, which is the case here, or you can pass, which is the case here, or you can pass an account from that already exists somewhere in the blockchain, so a temporary account that has potentially a bunch of proofs. And so you give it an offset. So it tries to borrow that as a read-only account. It tries to read, so that's an offset that you pass as part of your instruction data, the input to the instruction. It tries to read in the data field of that account an offset that tells it, and it doesn't care if it owns this account or not. It could be any account, right? We just need to read from memory somewhere. And it tries to read it at that offset, and it uses that to verify a proof. So that's the first tweak. You can either read the proof from some account somewhere or from the instruction inputs. And the results of the, if you pass a context state account, which you externally allocated yourself, but you transfer the ownership to this account, the ZK-El-Gamal-Proof program, so that it can mutate that account. That's important. And of course, if you can mutate, if you can store it in any account, that's a vulnerability, because then you can store the fact that you verified a proof when it's not true. So here you have to go through that ZK-El-Gamal-Proof program. If it verifies a proof, so we verified it here by calling verify proof. If the proof validates correctly and that function didn't return an error, then you can save it as in this context state account. So we can look at it. What are we doing? We look at whatever is the account. We try to borrow it. We check the owner, so we want to make sure we're the owner. This is not really essential, because if we're not the owner at this point, if the program here is not the owner, it's not going to be able to mutate the account. So it's more important to check that when you're just reading from something, because you don't want to read from data that was initialized by someone else. You only want to read data that was part of your state machine. Wow, this is so sensitive. So you're checking that the proof type is uninitialized. So you want a bunch of zeros here in this account. So you haven't touched it yet. And then you set the data to this thing, which tells you, which encodes the proof type and the context data. So the public inputs. And then you can close that account later to get back the rent. And so that's what I was showing here. If you don't pass an offset, you have to pass an account of that context state. And then it will read from the account. And it will make sure that this account is owned by the ZK-El-Gamal program. So it's here. Check ZK-El-Gamal-Proof Program accounts. You can check here. You will check that the owner of that account, the context state account, is indeed the program ID. The program ID here, which is ZK-El-Gamal, it's something that's hard-coded. And then it will extract the statement from the data in this account. All right, so that's what I wanted to say. There's no verification of proof that happens in the Token 2022 program. Just to reiterate that. It verifies, or it indirectly verifies proofs when it needs to verify a proof by checking if there is an account owned by the ZK-El-Gamal-Proof program that has the correct proof type, and then it extracts the statement. Or it checks if in the same transaction there is another instruction for the ZK-El-Gamal program that and then extracts the context or public input from that. The fact that this instruction exists means that, by the way, let me take a note here. I want to also make sure that this instruction is for the correct account, which we need to verify. All right, so the fact that this instruction exists that was calling the ZK-El-Gamal-Proof program and is the correct instruction for the right proof type, and the transaction didn't abort, means that the proof was verified correctly, and you can trust that statements that you extract from the inputs of that instruction. We can look at that, but actually I remember now I think it's here. Yeah, in the decode proof, we check that the instruction is actually for the right program idea. Because if you were reading, the instruction for like any program, I could have created my own program with bullshit, and here I could write anything, and that wouldn't mean anything. Anyway, let's go back. I think this is basically going to be the end, but I just want to look at some of the functions there and show you the patterns. So let's look at transfer maybe, because this is the main function and it's interesting. Transfer does stuff, but you can imagine that all of these functions do the same kind of things. It reads from the accounts that were listed in the instruction. So it just reads the next account. The first account is going to be the sender. The third account is going to be the recipient. Whatever, that's the schema. Could have been the other way around. And the second account is going to be the mint. So that's the token configuration. We check that the mint is owned, which here is important because we're only reading. If we were mutating the mint, then that check is sort of redundant. But since we're reading from the mint, it's important that we're not reading from like some arbitrary memory space, but memory that's owned by the Token 2022 program. So we know if it's owned by the program, it was initialized correctly, or the state is not an invalid state, right? It's part of the state machine. Then we borrow it, we unpack it, meaning there's an unpack uninitialized. So this will make sure that it has been initialized. So we're unpacking what looks like a pod mint. Pod mint is the mint. which tells you the supply, like stuff like that. That's the base token. And then we get the extension posable config, which is another extension just to make sure that the mint hasn't been posed. So that's the interaction with other extension that I was talking about. Then we get the extension confidential transfer mint. So that's the confidential extension. We'll do something after with it. Then we want to check if there is an authority. Oh, no, sorry. Here we cut into two branches, if and else. Here, if the base mint here has a transfer fee configuration, then we're gonna have to handle, does not, because there's an error. Then we're gonna have to handle fees. We're not gonna have to handle fees. But in the else branch, there is a base configuration for fees, so we're gonna have to handle fees. So there's two branches. There's like hooks. That's not too important, so I'm not gonna talk about that. Okay, let's look at the branch without fees because it's easier to understand. What we do here is that we call verify transfer proof. We always have these massive verify functions that basically are wrappers to verify a bunch of proofs. Here we verify a Ciphertext-Commitment Equality proof and a batch group ciphertext 3 handles validity proof data. That's a handful, but that's where we verify. Oh, and there's a range proof. And then once we verify all of that, we're going to create one context. The type is here. That contains a bunch of public inputs from these things. And before we expose stuff, we're going to verify that the different contexts, so the different public inputs for the three different kind of proofs that we verified here, are somewhat related or correctly formed. So I don't know, maybe here we check that the public key from the first proof, the public key from the first proof is equal to the first public key from another proof. And I can explain that in more detail, but I just want to keep it high level now. And for the range proof, we check that the range proof is aggregating a bunch of range proofs, by the way. So here we check that the first range proof is going to be for 64-bit range proof, then a 16-bit range proof, then a 32-bit range proof, then we need to pad because we always need to do a certain amount of this is part of the API. It doesn't matter, but this needs to sum up to 128 just because of the way things are done. And when we've done all these checks, then we can expose some of the public inputs that we're interested in. So some of the public inputs we're interested in, some of the public inputs are only here to be composed with other proofs, other sigma proofs or other range proofs. And so here in the transfer, you'll see that we're gonna eventually subtract to our balance, and what we're gonna get is gonna be a ciphertext. So we're gonna make sure that what we get is that. So this we need to export. So that we're gonna obtain something by taking our encrypted balance and subtracting the amounts, and we need to make sure that it gives us this thing. Again, this thing is gonna look like that. With a decryption handle, but we don't know the R here, so we cannot do a range check on that, a range proof on that. So we're gonna re-encrypt it under another one, R2 times H, where we know the R2, because we want to do a range proof, because we want to prove that when we subtract the amount from our encrypted balance, it doesn't give us something that's huge, meaning that we had the balance, we had the funds to pay that transfer. This one is gonna encrypt to 3 different public keys and prove that the encryption is correct. And that's gonna be the transfer, by the way. So we're gonna have to prove that low plus 2 to the 16 times high is equal to the transfer we're making. I don't know where this is done. And that's, yeah. And we're going to encrypt that to 3 different destinations. We're going to encrypt that to ourselves. So this is checked here.
We're going to encrypt that to the recipient because they need to be able to decrypt that balance eventually. And we need to add that to their pending balance as well. And we're going to encrypt that to an auditor in case there's an auditor. If there's no auditor, then this will do nothing, basically. And this is the commitment. So this is a unique, again, this is going to be like X times G plus some R times H. I'm using the same R, but you can imagine that it's a different R from here. Yeah, I guess this is X1, X2, but it doesn't matter too much. And then we're going to prove, this thing is going to come like that. And it's going to have D1, D2, D3, 3 decryption handle, 1 for each public keys. And you can imagine that D1 is going to be R times first pub key. So we were proving that we've done that correctly. And then the range proofs, you can see we want to prove that the remaining balance, so our new balance hasn't like gone into the negatives. So it's going to be 64 bits. Then the transfer amount, the low part is 16 bits, and the high part is 32 bits. That's what we're proving. But that's it. Okay, so if that doesn't make sense, just replay that. I didn't want to go too much into the details here, but I guess it's interesting to see at least one of them. And let's go back to the mother transfer. Where is it? It's here. So we got that context, and then we're going to check that we have the authority to move funds from that token. So the authority is just going to be another account, a system account in Solana. Everything's a system account, but that's a system account. And we're going to check that, I guess it's inside a function, but we're going to check that this is a signer essentially. Maybe I'll showcase that to you, but I can tell you in advance that this is a signer and that this owns the token account that is sending money. This is just some auditor stuff. So we're going to ignore that because it's not super important. Yeah, so let's look at process source for transfer, and there's also for the destination, that's interesting. But for the source, you can see that it will check that the source is owned by this program. It will check that so we look at the data field of that account, of that source account, and we get it's supposed to be a pod account, right? And then we can look at some extensions. These are not interesting, or some base property. We want to also check, of course, that the base mint of that token account is the mint that we're looking at, because we're using the configuration of that mint. But what's interesting is going to be valid as source. Oh, this is not interesting. Oh, here's the check, right? We're looking at in the proof statements, the source public keys that we use is the El-Gamal public key that's in that token account. And where do we verify that it's a signer? Oh, it's here. So this function is basically going to verify that the token account, the owner of that token account, is the authority that we passed, this other account that we passed. And potentially that other account is going to have to be a signer unless we're dealing with an account that's a multi-sig account. But I'm not going to talk about that branch because it's not very interesting. But it has to verify that some account is a signer. So that's what I mentioned earlier. And I just want to show you the arithmetic that happens. So we're going to update that sender balance. Here we can update directly the balance, not the pending balance, because we know exactly how much we're sending. And the balance that we're sending is going to be this homomorphic subtraction between the initial balance and these two chunks that we're sending. And you can see in this function, it's like the low chunk. The low chunk here added to the high chunk that was shifted by 2 to the power 16. And when we're handling the ciphertext, you can imagine that everything here is really two parts. It's like something that looks like a persistent commitment and something that looks like a decryption handle. And these will be, you can homomorphic add everything, and everything will work. Okay, should I stop here? I think that's a lot. I mean, we can look at, but every process function basically looks like that. They unpack accounts, they make sure that we own these accounts, they make sure that everything makes sense, and then they do homomorphic stuff and they verify proofs. So maybe I'll stop here. Yeah, maybe I think I'm gonna stop here. I think that's a good place to end. Yeah, if you have any question, feel free to ask, I guess. And thanks for watching until the end.